Okay, so last time we started the topic of graphs, right? And we were discussing some of the properties of graphs and how can we use them as a tool in physics to understand the relationship between two quantities, two or multiple quantities. There are three-dimensional graphs as well, so you can also see three relationship between three quantities, and so they just give you a visual representation of what's happening, right? Or at least they can try to give a visual representation of what is happening. From there, we talked about displacement time graphs, and we discussed various graphs, the various shapes of the graph, and what do they tell us, right? So for example, the first graph that you can see over here, this one shows you that we see a straight line. This is a displacement time graph. So displacement is 10 at every instant of time. It does not change. So if displacement is not changing, what does that tell you about some other quantities, such as velocity? Velocity is change in displacement per unit time, but displacement is not changing, so velocity becomes zero, right? And so you can get that as also by taking the gradient, mathematical gradient of this line, as in change in the y-axis divided by change in the x-axis. But you see that in y-axis, the line does not change. It is straight like this. So that is zero, and that's why velocity is zero. This graph shows you a linear increase in the displacement of an object, and so you can see for every increase in this time there is an equal increase in displacement. So here S2 is bigger than S1. So if I find the gradient of this graph, which is always velocity, it would be greater than zero, because S2 minus S1 is greater than zero. It's not negative, so it's a positive number. Similarly, we had this thing: if the curve goes down, then it's just the opposite of everything that we discussed in this one, right? So yeah, I think did we did more? No. So so any questions from this thing so far?
No, sir.
Okay. Okay, now there are also graphs that show you the relationship between velocity and time, and these are called the velocity time graphs, right? So first, let's look at what informations can I get from this type of a graph. So suppose if this is time, thing that looks like this, right? Again, here is pick 2 points, this one and this one. Suppose this point is V1 at T1, and this point is at T2, we have some V2. Now, if I find the mathematical gradient of this line, which is m change in y over change in x, y is what? Velocity. So it is change in velocity. Divided by, on x, we have time. So it is change in time. V2 minus V1 divided by T2 minus T1. But what is this? What is this equal to? What physical quantity does this represent?
Sir, acceleration.
Acceleration. So the gradient is the acceleration of the object. There is one more thing that we can find in these type of graphs. We know, so we have two quantities, velocity and time, right? How can I arrange these quantities such that I get something different from acceleration. Well, you can arrange them v by t to get acceleration. What else can you do? You can multiply these two quantities, v times t, but what is that? Remember, velocity is displacement per unit. Exactly, right? So this would be a displacement. So which just immediately tells you how can you get v times t, right? Any v times t by finding the area under this curve or graph or line in this case, right? So the area under this, so for example, if this is a triangle, right? Suppose this is a triangle, the area under this triangle is given by half into base into height. So it is half into the base is time axis t, height is the velocity axis times velocity. So this is half v times t. So v times t is displacement. So you can see that the area is giving you the displacement of the graph. This half is also included. It is a multiple of velocity. So this is your displacement. Okay, so is that clear?
Yes, sir.
Okay, so I'm not going to discuss the stationary velocity case or anything, or would you like me? Would you like to discuss that as well as we did in this displacement? Because it's just the same, right? You just pick any velocity and just draw a straight line from it. Suppose I take this, I draw a straight line from this one. At this straight line, there is no change in velocity as time increases. So the change in velocity is zero, which means the acceleration or the gradient will also be zero, right? So, but you can see that the area under this line is not zero, right? There is some area because of course, and you should expect there to be some area as in some distance covered because it is moving with some velocity. It's just that the velocity is not changing, but the object is still moving, right? So that's this is the acceleration equals zero line. Okay. Okay, now we haven't looked at any curves in these graphs. Let's come to that part. And so basically we are return back to graphs, as in just the mathematical definition of these graphs, right? So okay, so remember here we were talking about graphs, right? So I drew some lines. Some of them were weird looking, and it just told you what does it gives you. So it gives you the relationship between two variables in a space, in our space of real numbers. Okay, so let's return back to that thing and let's discuss some more properties or some more stuff that makes up graphs. The first thing is, suppose if I have, so what we're doing is we're discussing gradients. So if I have this thing, this line, what gradient would you expect this line to have? So let's just draw these lines here and write down the gradients of these. What would you expect it to have? You see, at every point, the line is still the same. So this point lies, suppose, on this value. So it lies here. So these are multiple values up and down. But you see, at every time instant or at every point, this dot is here, here, and here. So it lies on the line, right? So if I take the difference between the two, you just get 0, right? So the gradient is 0. This line is exactly how we saw this line. So it means that for any physical quantities, if you have a line that looks like this, the gradient of that line is 0, right? Is that clear?
Yes, sir.
Okay, so now suppose that you have this line, right? Like this. This is your line. What would you expect the gradient to be? Just tell me if it should be greater than, or less than, or equal to 0. Which one should it be?
Greater than 0?
Greater than 0, exactly, right? So you can mathematically see that as well by taking 2 points. Suppose we take these 2 points. Suppose here we have T1, S1. Suppose we're talking about displacement. Here you have T2 and S2. Given that, you can see obviously S2 is greater than S1 because S2 is above it. So given that S2 is greater than S1, the gradient is change in S, which is S2 minus S1 divided by T2 minus T1. If S2 is greater than S1, then this term is always positive or greater than 0, right? So hence the gradient in this case is greater than 0. Another easy way, another way of is telling that if it should be positive or negative is by this analogy of angles, right? So suppose you just draw a horizontal line like this, and then you put whatever line that you want to see what's its gradient, well, whether it's 0, positive, or negative. So in this case, suppose this line, so you just put it anywhere on this. So you put it like this maybe, and then you see the angle from horizontal. If the angle is going in anti-clockwise direction or like this, then you can see that the gradient is positive in that case. So the gradient is positive. If I have a line that looks, so again, I have horizontal, I want to draw a line on it for whose gradient I want. Suppose it is like this. Then you see the angle goes from this line. Well, really it is like this, but the one that you can draw just from this horizontal to this line is in this direction, which is clockwise. So in this case, the gradient is less than 0. And if on this horizontal line, I just draw this line or this horizontal line, then you see that the gradient would be 0 because there is no angle between the two lines. Okay, so that's your straight lines. What about, there's an interesting one. What about this one? What would you expect this to be, the gradient of this line to be?
Would that be 0 as well?
Okay, well, not really, no. Let's see. Just tell me, so again, the gradient would be 2 points on this line. Suppose and the gradient m is change in y over change in x. Y is the vertical axis. So you see that in vertical axis, there is some y2 and some y1. So y2 minus y1, that is not 0, right? But about change in x lies on this thing, right? On this axis. So suppose if this was my axis, y and x, then this line that we're talking about, at every instant, it is just at x. So at this x, it has y1, y2, and so on. So the change in x is 0. There is no change in x happening. Acha, now this gives you something that is called infinity. What does this infinity really mean, right? Let's just in very short detail just discuss that. uh, so when we say infinity, we just mean that it is undefined. Really, it is not defined at this value. For example, in this case, it is not defined because suppose this is your graph. Let me draw it over here. Okay, so this is your graph, and if I draw a line on it, which is this one, right? And suppose on this axis I have time, on this axis I have displacement. You see that at this instant of time, let's call it t1, you have infinite number of values for displacement from here to here, right? Why do I say infinite? Because I mean, of course you could say no, it is finite, because maybe this is one, then this is two, then this is three, so we know the number. But it's not that simple, because uh, it is a straight line, a continuous straight line, and we know there are decimal values as well. So it could be I mean, you never know where you could start from. Maybe you start from 1, then the next value could be 1.000000000, and like something like this. Then the next one could be 1.00, everything the same, and then 2, and then increase, and then this value starts increasing, and then this, and then eventually this becomes 2, right? And so this is how this is why there are infinite values that live inside this on this line at a particular t1. So you don't know what displacement am I talking about. I'm talking about this one, this one, this one, this one. I'm talking about infinite displacements, which is why anything divided by 0, or in this case, this y2 minus y1 divided by 0 is infinity, right? Because there are infinite number of values on this line uh, for displacement at t1. Okay, so was that clear? Is it clear?
Yes, sir.
Okay, so next let's look at curves. And their gradients. Okay, so we could have a curve that look like this. And so what would you expect the gradient of this curve to be? The first thing is that for curves, gradients are defined at different points. As in, at different points, you're going to have different gradients, right? And you can see why. Because for a straight line, every point lies same on this line. It lies like this. So there is no change in those points. But for a curve, the points are changing. At one time it's here, at some other time it is here, right? So it does not lie linearly on the line, you could say. And so for every point, what you can do is you can draw a tangent, something like this, right? Let's give it some other color. Okay, so you can draw a tangent at every point on this curve, and you can see what the gradient is. Now you can just go back to your understanding of this thing, that a line that goes upwards like this always carries a positive gradient, while a line that goes downward like this always carries a negative gradient, or has a negative gradient. In this case, you see the line is going up. And in fact, if I want to draw this much better, let's just draw the same curve again, right? You can see if I take this point, I can draw a tangent like this. Then I take this point, I can draw a tangent like this, and I can take this point and I can almost, the tangent, you can see it's becoming vertical. Well, this is not in. Right. So what do you see? If I draw a horizontal line for all of them, just to check my angles, this line has an angle, while this line has a greater angle. And this one has even a greater angle. Right? So this, if this is θ1, this is θ2, and this is θ3, then clearly θ3 is greater than θ2, which is greater than θ1. Achha, this tells you that the you can see at every point on the graph, the gradient is different. So on a curve, the gradients are defined at each point. So the gradient for this shape is going to be a positive gradient. That's something that we can for sure tell by looking at the graph, that it will be a positive gradient. Okay, so now suppose I could also have a shape that looks like this. Again, by the same reasonings, see the gradient here is like this. The gradient here is something like that. Well, let's just assume that it lies on the point, right? And then at this point, it is like this. Acha. So for these, you can see that the lines are going downwards. So if they're going downwards, we know that the gradient for this will be less than 0. So it would be a decreasing, well, it's not decreasing, it's increasing in the negative direction. Okay? Or you could also say it is decreasing, but you could say that it's really increasing in the, why do I say increasing in the negative direction? Why am I arguing with this logic that, you know, you cannot say decreasing, but it's better to say increasing in the negative direction? Okay, so the reason for that is, look at the line, the curve originally that we're talking about. Its direction, the arrow is telling you the direction. The direction of this curve itself is going down, meaning this line is going downwards. And if the line is going downwards, its gradient is increasing downwards. But to cater for this downwards, we add a negative sign to that. So the gradient is less than 0 as a negative, but it is increasing. So it means it is increasing in negative direction, right? Okay, so there's another one, the other shape that looks like this. Like this. Achha, is in this one, you see that you can have these points and draw tangents at these points firstly. At this point, tangent is almost horizontal. Okay, so what is happening for the gradient in this one? In this case, what is happening to the gradient? The line is going upwards, the curve is going upwards in this direction by the arrow, shown by this arrow. And you can see the tangents on this curve are becoming horizontal with time. Slowly they're becoming horizontal. And at this point, it's completely horizontal. So what is happening to the gradient? It is any guess? Okay, so the gradient in this case, as you can see, the tangents are becoming straight or horizontal. So remember, for this line, we saw that the gradient becomes 0. So the gradient is going towards 0. And how are we going to do that? By decreasing. So the gradient is decreasing in this case. So it's a positive decrease. Then you have another shape, finally, that looks, well, something like this. For this one, you see that the line is going downwards, and the gradient at each point is also going downwards, right? And then eventually it becomes horizontal. So the gradient in this for this curve, you can see the tangent is decreasing. The tangent is becoming horizontal. So, but the line is also in this direction, downwards direction, going in the downwards direction shown by this arrow. So the gradient here is decreasing, but it is less than 0. So it is less than 0 and decreasing. So meaning it is negative but decreasing. Okay, so is that clear?
Yes, sir.
Okay. Okay, so let's come back to displacement time graphs. Right. And now what I'm going to do is we're going to discuss these graphs. What do their gradient represent, and what do they tell you about the kinematics, right, of the situation? So let's draw again a very simple one. Or let's make it even more simpler. Let's draw it on this line. Right. So you see this orange or pinkish, well, pink line. This is what we're talking about, and at this point it is 0. This is time, and this is displacement. Okay, so, well, this is what you have, and what we want is, I want you to tell me its gradient and what is happening kinematically. So the kinematics, as in the motion, right? What is happening to the motion? So first, can you tell me what would be the gradient of this line, this pink line? Any idea? What should be the gradient of this line? It would be a 0, right? So it would be change in s by change in change in t, which is m equals 0. Okay, what about the kinematics? What's happening kinematically? Well, you see that the gradient is 0, but that is what? That is just the velocity for a displacement time graph, which means velocity is 0. So kinematically, the material or object is at rest. It's not moving at all, but it's at rest at this origin, right? So not at some displacement, because on the displacement axis it lies still at 0. So the kinematics is that the object is at rest on origin. Okay, so then let's draw another one. suppose you have something like this. Again, this is t and this is velocity. So you can see in this also, I want you to tell me the gradient and the kinematics. Well, the gradient of this line is still 0 because at every instant of time, velocity is just at some same value v1, let's say. So at every time interval, it is the same value. So change in y by change in x, because change in y as in change in velocity is 0, so the gradient is 0. What about the kinematics? Kinematically, what is happening?
Constant velocity.
Not really, because again, why not? Because this thing, the velocity at every time is the same, right? At every instant it's same. So change in velocity by change in time, change in displacement by change in time. Oh, sorry, I drew velocity, right? Yes, my mistake. This was displacement, right? And this is some value for S1. Sorry for that. Yeah, so in this now, what is happening kinematically? Displacement is not changing, right? So the object is at rest, right? Velocity is 0 because displacement is not changing. So object is at rest. But this time, how is it different from the above one? Above one, also the object was at rest. In this one, how is it different from that? It is still at rest, but it has covered some distance initially. So it's like this, that this is a track, and this is 0 meters. So a person starts from here, and then he runs, jogs up until this point. Let's say this is some S1. And now he just stands there, right? So this one, the person was initially at rest as well, right? So he was at rest, his velocity was 0. Here also its velocity is 0. So in the second one, where the person is at S1, is this for this graph. So he has covered some distance, but now he's at rest after covering that distance, right? So is that clear?
Yes, sir.
Okay, so the object in this case is at rest ahead of origin. Okay, let's see how much time do we have. Okay. Now let's draw another one. Okay, this is your graph. This is displacement. This is time. So first of all, what is happening for the gradient? The gradient of this line would be what? It is increasing, right? So the gradient is increasing. At every point, there is an increase in displacement as time increases. But the gradient is constant. At every point, the gradient is the same, which means that it is a constant. Kinematically, what's happening is, because you can see the displacement is changing. So that means the object is moving. That's the definition of moving, right? Change in displacement. So the object is moving, but the change is same at every point, here, here, here. So I can pick any point on this graph and calculate the gradient for them. I would get the same answer whether I pick this one and this one or this one and this one. Doesn't matter what point I choose, I get the same gradient. So it is moving, but, or you can say it's moving with constant velocity. Right. So is that clear?
Yes, sir.
Okay.